Alrighty, let's look at the compressible version of the conservation of mass. We said incompressible means non-divergent flow as a good approximation. Compressible fluid, the main thing to remember is that what we have said before is still true. Density is an inconvenient variable. It's a well-defined concept but for measuring density there is no direct way. So we want to be able to replace it with something that is directly measurable, right? And of course, in the atmosphere, we have our favorite hydrostatic balance, where which allowed us to write things in the pressure coordinate equations in the pressure coordinate, right? So we defined z as a function of x, y, and p. Right? Then delta z is of course delta z over delta p times delta p. Okay? This is just inversion of the dp dz, which is going to take us to obviously hydrostatic balance. So delta m, the change in mass, is rho delta x delta y delta z, and rho is you can write this as 1 over dp dz. So delta x, delta y, delta p. So we just used this to replace delta z with delta p. That's all. Nothing really changed. Now we can use hydrostatic balance to replace rho 1 over dp dz by minus 1 over g. Okay? Be very comfortable with this. dp dz equals minus rho g. That's all we have used here. No big magic, except we have delta p instead of delta z, and delta m has suddenly become very simple. It's just a function of gravitational acceleration and delta p, both of which are easy to deal with, right? So we went from density into pressure with gravitational. So we used dp dz plus g rho equals 0, and now we can write the continuity equation or the divergence equation as grad p dot up equals du dx plus dv dy plus dw. Often it is pronounced as omega. You can see that's not exactly w because the vertical velocity. We will not get into that. We'll just call it w for now. dw dp equals 0. Okay, continuity equation in the pressure coordinate now is much simpler. We did not make any assumption about density being constant. Okay, we are simply replacing density with pressure. Density depends on pressure and temperature still. It's compressible, but by writing it in the pressure coordinate, we have made the equation look so simple, quite parallel to our non-divergence equation for the incompressible fluid. Okay, this is the trick that really helps when we move to the pressure coordinate. Okay, now you know the density being absorbed into pressure via the hydrostatic balance gives us this similar looking equation as the compressible and incompressible fluids, except you have to remember that the grad and gradients and derivatives are in the pressure coordinate for a compressible fluid, and for an incompressible fluid it's still fairly straightforward. So just remember, density has to be dealt with some way or the other. Moving to pressure coordinate helps us, because as we have said before, measuring density is hard, but even measuring height in the atmosphere is not so easy, right? You need some way. Well, now you can do it with GPS, I suppose, but if you are sending a balloon, or if you are in an aircraft measuring things or whatever else, if you're in a mountain, measuring temperature, pressure is very easy, whereas measuring height and density are not easy. This is the reason why we move to pressure coordinate, but it also makes the equation look so simple and nice. Okay, We still have to solve the nonlinear equations, but now we have the equations of motion, momentum, and conservation of mass. Now we need thermodynamic equation to complete the set of equations of motion, right?